Hello, my name is Ehsan Shahri, and I'm currently a postdoc researcher at the University of Aveiro, Portugal. Today, I'm excited to share with you the core contributions of my doctoral research titled Software-Defined Networking for Holistic Communication Management and Cyber-Physical Protection Systems. In today's Industry 4.0 landscape, systems are becoming smarter and more interconnected. At the core of Industry 4.0 is Industrial IoT, where sensors, actuators, and intelligent devices are networked to support industrial operations. But with this comes a major challenge. The network must deliver reliable, low latency data, even in dynamic and resource-constrained environments. Think about robotic arms working in sync or mobile robots navigating a factory floor. Even small delays can cause errors or safety risks. The current networks and application layer protocols don't fully support these real-time requirements. Within application layer protocols, MQTT or message queuing telemetry transport is widely used in IoT and industrial IoT because it's lightweight and efficient, ideal for low power devices. But while MQTT supports message delivery reliability throughout quality of service levels, it doesn't guarantee timing. That means we can't control when the message arrives, a serious problem in industrial systems that rely on precise coordination. So my research focuses on extending MQTT to support real-time communication while keeping it lightweight and scalable. To address MQTT limitation, we integrated with SDN or software-defined networking. SDN gives us a centralized programmable control over the network, allowing us to reserve bandwidth and prioritize time-sensitive data flows dynamically. Imagine a smart city like this figure. MQTT is like a road system where all data travels the same way. Even urgent messages like ambulances can get stuck in the traffic. So with SDN, we add a smart traffic controller that detects urgent vehicles and they clears the path so they arrive on time. In the same way, real-time MQTT plus SDN ensures real-time messages don't get delayed, which is critical in industrial environments. Here's how the full system comes together. We integrate SDN with MQTT to bridge the gap between flexibility and real-time performance in industrial IoT systems. The proposed architecture is modular, standard compliant, and deployable on existing platforms, making it compatible with widely adopted IoT and industrial IoT protocols. So this work represents the first integration of SDN with real-time enabled version of MQTT. Our main contributions are developing a modular SDN-based framework to manage real-time MQTT, proposing a set of real-time extensions to MQTT. We named it RTMQTT, and finally MRTMQTT, a multicast enhanced version that improves scalability. These extensions are supported by schedulability analysis, helping guarantee deterministic behavior even in large-scale industrial IoT systems. Here's a closer look at how the RMT MQTT architecture works. It includes MQTT clients as IoT devices, MQTT broker, a real-time network manager, and some OpenFlow switches controlled using Rio OpenFlow controller. In a basic setup, subscriber 1 and subscriber 2 subscribe to a topic published by publisher 1. With a standard MQTT represented by blue lines, the message is routed without any notation of time sensitivity. In contrast, RTMQTT operations, represented by green lines, allows the publisher one to include real-time requirements in the message using the MQTT user properties field. The real-time network manager receives these requirements and communicates with OpenFlow controller, which install flow rules across the network to meet timing requirements. We validated our architecture both in emulation and the real hardware. First, we used the Mininet, a powerful SDN emulator, to simulate large and dynamic topologies. Then we built a real-world testbed using commercial off-the-shelf hardware, including two edge core bare metal SDN switches. This hybrid setup helps us validate both scalability and practical feasibility under real conditions. We tested the system with both normal and time-sensitive MQTT traffic. across three network slices and three load levels. As you can see in the plot, the blue boxes represent normal traffic, while the yellow, black, and red ones show time-sensitive traffic at different priorities. Without our real-time extensions, normal and time-sensitive traffic experiences similar latencies, showing no prioritization. But with real-time extensions enabled, we see a latency reduction for time-sensitive traffic, especially the highest priority, the yellow one, achieve latency reduction up to 40% even as the load increases. The results show that our approach enables traffic prioritization, segregation, and most importantly, predictable latency even under load. To validate the real-time behavior of RTMQTT, we formalized its system model using a fixed priority, non-preemptive scheduling policy with first-in, first-out strategy. We analyzed it with two approaches, the holistic approach and trajectory approach. As you see in this figure, we break down the response time into three parts, from publisher to broker, inside the broker, and from broker to subscriber. Since the communication delays in the first and third part are similar, we focus our analysis on the path from publisher to broker. As you see on the right, both trajectory approach and the holistic approach compute upper bounds for worst case response times that are higher than those measured experimentally. Now that we've seen RTMQTT, let's move to its extended architecture. MRTMQTT, which enables real-time and multicast communication across multiple edge networks. In this example setup, publishers in edge network A publish two topics alpha and beta, while subscribers in edge network B and C subscribe to both, each with different real-time priorities. Real-time network manager in publisher side first collect timing requirements from publisher using MQTT's user properties and then forward these requirements to the OpenFlow controller. The same operation will be performed in the subscriber side. Then OpenFlow controller will select a rendezvous point, build a multicast tree, set up multicast group, and finally configure the switches accordingly. If topic quality of service level is set to 0, data is sent directly from the publisher to subscriber. When the quality of service level is set to 1 or 2, data is first sent to the broker on the subscriber side and then forwarded to the subscribers. In this experiment, we validated MRTM-QTT using MiniNet emulator with the goal of evaluating a multicast performance. We designed a realistic topology composed of 8 OpenFlow switches across 3 edge networks. The setup tested the system under 3 different load levels and with heterogeneous data streams, simulating typical industrial IoT traffic patterns. In the final set of results, we evaluate MRT-MQTT against a standard MQTT and direct multicast MQTT, the only comparable work available. We focus on worst case latency distribution for time-sensitive messages. As shown in the left graph, MRT-MQTT achieves the lowest latency across all scenarios thanks to real-time prioritization and multicast support. This confirms its ability to segregate traffic and maintain predictable behavior even under load. On the right, you can see the MRT-MQTT also reduced bandwidth usage by about 58% for quality of service 0 and 45% for quality of service 1, making it more scalable for large deployments. To wrap up, this research extends the state of the art by proposing a scalable real-time MQTT framework tolerated for industrial IoT applications. Its impact serves a dual role. It addresses today's critical needs like real-time guarantees and heterogeneity, and it lays the groundwork for future-ready systems. The architecture is modular and compatible with advanced networking technology like TSN, P4, and hard real-time Ethernet switches. It also opens up opportunities for future research on SDN-based security mechanism and controller optimization strategy, enhancing the framework's adaptability to evolving industrial IoT demands. Thank you so much for your attention, and I appreciate your time and interest in my research.